Welcome all to the panel discussion today, lightning speed to market using digital tooling at CDP. We'll be sharing a few techniques, how we do some very fast injection moulding on site here at CDP. I will go through a short welcome to CDP. I will introduce our panel here today. We'll give a short introduction to the topic, and then amongst the panel, we'll be going through a number of questions that have arisen here, and we'll use those questions to tell you about the technique and how valuable it's been to us, where there may be limitations, and you know how we use that service, how it speeds up and benefits our clients. So I think without further ado, I'll jump in. So welcome everyone. First up, CDP, we are a innovation partner, and we help from the front end of innovation to pilot manufacture. So we can help people work out what the right product is, the right market, and what needs are best served by that market. And then we can take people through the journey of prototyping and development, choosing the right technologies, all the way through to pilot manufacture, where we help people with their design history files. We help people with the assembly or the manufacturing processes in preparation for full launch. We do this with a multidisciplinary experts, and we work this in industry of healthcare, consumer, and industrial sectors. Through that process, we use prototyping significantly. We're aiming to bring reality to our projects and quickly assess what works and obviously what doesn't. I'd like to introduce my panel. I'll start with myself. I'm Jez Clements. I'm a mechanical engineer. I'm one of the directors at CDP and have been working here for the last 15 years on projects from sort of things like insulin delivery all the way through to hairstylers and in consumer worlds. I'd like to introduce my colleague, Josh Lanson-Miller. Josh is a consultant design engineer. He's been one of the champions of the process internally and has helped develop this process and roll it out as a tool for our employees. I'd like to introduce James Davies. James is a senior consultant mechanical engineer. He's a technical leader and has been deploying this process in areas like auto injectors, and has been one of the main users of the system. I'd also like to introduce my colleague, Tom Britton. Tom is a design engineer, again, a key user, and through that use has helped pioneer and develop the process. As a fun fact, Tom does have an explosives license, but we haven't had need to use that on this project. So again, just for any late joiners, we're going to dive into the topic in a minute. And then please log your questions in the side. We'd be happy to answer those towards the end, but we'll go through a panel debate for the next sort of 40 minutes. Okay, so as an introduction to this topic, in the development industry, we use hundreds of prototypes through the innovation programs that we undertake for our clients, and our clients mainly are in the healthcare and consumer sectors. Most of our work is in handheld devices or body-worn devices, but mostly it's that sort of handheld size of portable units. We are constantly searching for new ways to create new products more quickly and efficiently. This is particularly challenging when component design becomes highly optimized. For example, during complex medical consumables, where material compatibility and secondary assembly processes such as welding or plastic forming in some way are needed. We really need to work in the right materials as soon as possible to learn what will and won't work. The problems we normally encounter in prototyping are the traditional time, cost and accuracy, and getting into the correct materials. Our solution to this has been to try and get to accurate injection molded components in the correct material so that we can fully test the final design. By making them at the earliest point in the development process, we found that we've reduced time to market and optimizing the final components as soon as possible enables us to go through those iterations of a design cycle and the typical iterations of things like a works like, looks like, and even getting to those made likes. We're getting there as soon as possible in the design cycle. And my colleagues will be talking you through this process for the next 30 to 40 minutes, and then we're very happy to hear your questions. So moving on, I will pass over to Josh. Josh, you've got a video you can share, so probably gives a great context to explain exactly what we're doing. Over to you, Josh.
Thanks, Jez. Hopefully everyone can see a picture of a hand holding a syringe. Let me know if you can't.
No, that's clear. We can see that, Josh. Thanks.
Super. Okay, so I'm going to use this example to help explain the process. It's a multi-dose syringe, and all the white plastic parts were created using the digital tooling process. And I'm going to focus on that central barrel holder, so that's the cylindrical part in the middle. Okay, so the tool stack itself is quite simple. You've got a fixed half on the right, moving half on the left. We inject from the fixed side, and the moving half contains a tapered pocket, and that contains our 3D printed cavity geometry. So the 3D printed geometry, I'm just going to pause it here. So this is a set of blocks that form a 3D jigsaw. And the way it's divided up is to do with what would normally be, say, an action in a tool or a moving part in a tool. And that allows us to have quite complicated geometry, and it all comes together to form this sort of what I'll call a 3D printed sort of 3D jigsaw. So those parts are all fit together, and that then fits into this tapered pocket. So then you fit it, the tool closes, and then you inject your plastic, whatever that might be, and then the tool will open, and we then release the part by hand. So it's hand fitted, and then hand assembled, fitted, and then loaded. And then you disassemble the tool and your parts left behind. So it's quite a simple approach to make what can be quite complicated components. So hopefully, and I'll pass back to Jez. And do ask any questions as we go through this. I'm sure there are some.
Okay, yeah, thanks for the overview, Josh. James, you've been using this technique through a number of projects. How would you describe the benefits over conventional tooling in a project such as you've been running?
Oh, thanks, Jez. Well, yes, I think you kind of touched upon them in your introduction there. I guess the main benefit that this process offers is to fill the gap between sort of 3D printed components on the one hand and injection molded parts on the other. So, you know, typically 3D printed parts, which we use all the time in when we prototype parts, we can get hold of those within a day or so, or even less. You know, we can get them in the afternoon if we do a morning build. So we get those very, very quickly. Typically, though, even though the resins are representative, they're not the actual materials that we're going to make our production parts in. So they've always got this shortcoming that, you know, you're not quite sure how representative they are of real components that are injection molded. On the other hand, the injection molded parts that we would get, you know, typically you've got to get your design to a point where it can be tooled, and we'll release that design. And then it's normally sort of a 3 to 6 week lag between us releasing the design and getting the tools made, and then the first off parts off from the injection mold machines. So you've got that lag there with the injection molding process, which means you don't get the actual the correct geometry in the right materials for about sort of 3 to 6 weeks. And what this process offers us is the ability to get actual parts in the actual materials and the actual geometry within sort of a day or two. So it's got the same sort of time scales as 3D printing, but with the benefit that it's in the actual materials. So we don't have to wait for the sort of single cavity components to come in which might be 3, 4, 5 weeks away. And really, it's that time benefit that is the massive benefit that this process offers over both 3D printing and injection molding. And what I guess that means is because we can get representative parts in actual materials really quickly, it means we can then test those parts and we get much better test results, and we get those test results really quickly. So we can then iterate the designs and maybe try again, because we haven't invested a lot of money in making these tools. So, if we'd had metal parts tooling made, we'd have to invest quite a lot of cost in that. But with this process, we get a low cost parts very quickly, and that means we can take more, we can try more iterations, we can change the design, we can make new tools and get new parts and test them again. So the time it takes to do that iteration loop is very quick, and that means that we de-risk the whole project. Basically, we can get to confidence in our designs and confidence that we can make those designs really quickly, and before we go to metal tooling, which means that we don't have to do as many tooling iterations when we go to metal tools. So it's really about risk and speed. That's where the main benefit of this process.
And when you're making those iterations, are you printing new parts of the tool, or are you reprinting the whole tool each time?
Well, we can do it. I mean, it might be that we've got elements of the design that are maybe on just one core or one aspect. That means we can swap out just a section of the tool. But really, with a 3D printer, it's not a huge overhead to reprint the whole tool. So that's something that you can do overnight and come in the morning and have a brand new tool there. So I suppose it depends on the situation, but yeah, certainly it's something that we can do very quickly.
And those you mentioned getting to getting into the real materials. It's obviously the reality of the test there. Can you talk me through some of the properties where it's made a real difference in your project? What sort of learnings that wouldn't have been possible without this technique?
Yeah, definitely. So just talk a little bit about the materials, and really that's a key thing. So often, with prototyping, there's an element of uncertainty when you're using, say, 3D printed resins. You're not quite sure if the real parts are going to behave in the same way that 3D printed parts are. So what this process gives you is it opens up the entire world of thermoplastic polymers that you've got with conventional injection molding. So that's all the commodity plastics, the engineering plastics, and the technical plastics we can use within this process. And then we can use materials where we've had specific additives put into the polymer. So maybe there's been lubricants added to modify the plastic to make a low friction polymer, or maybe we've got a special additive that makes the parts X-ray opaque. Or maybe we've modified them with an additive so they've got the right electrical and thermal properties. So you've got all the materials open to you that you would have in actual production manufacturing. And what that means is your parts, not only are they the correct geometry, but they're also the right mechanical properties. They've got the right strength and stiffness properties that you would have in a production component. They've got the right surface texture and surface finishes that you would expect. They've got the same frictional properties, and that's really important if you're going to be doing testing of a mechanism, and it's sensitive to friction, and you want to know how it, that the test results are representative of a real production design. Then you get that with this process. And then the other great thing with this process is it allows us to do very specific polymers. So we can actually very, very early on in the design development cycle, we can test with medical grades of materials. So we might have picked a particular polymer that has got drug stability properties with a particular drug, or biocompatibility properties, and we can actually shoot that material into our tool and get that a part in the right actual material. So not only is it really good to get accurate mechanical testing, but we can then do, as we've done in the past, things like drug stability testing, and within a few weeks you're going to get sort of drug stability data from that component because it's been molded in the actual material. So that's that's certainly been really good in the past where we've done. I mean, the example that springs to mind is molding a septum, and we could then use the right elastomer material using this process, which then meant that we got drug stability data really, really soon. And we would have got that data, of course, had we got the parts injection molded on a metal tool, but we wouldn't have got that data for another, say, 3 or 4 weeks at the earliest. The other thing is with this materials is that we can also, as well as the rigid materials, we can also use elastomers. So we can use TPEs, which is great because it means we can do overmolding, which we've done using this process. And, that means we can test things like seals, for instance. We can also tackle the higher melt flow resins as well. So maybe not the really exotic materials like PEEK that have very high melt temperatures, but we can certainly do really most technical plastics.
I was going to ask, where do you find the limitations? The 3D printed parts aren't as hard as aluminium or certainly not as steel tools. Where do you find the limits with some of the materials?
Yeah, well, I think we, as I said, we can tackle most materials. We should be able to do things like glass filling as well. What I think essentially what you get with this process is you get a handful of parts, which is really all you need for doing early test work. And if you do get tool degradation, we can always really quickly print another set of tools. So I think that's how we can mitigate that issue.
Excellent. Tom, maybe you could share a little bit about how cost effective this process is, how we might go about running the process internally.
Sure. So it's building a bit on what James has sort of touched on already. Conventional injection molding, there's a capital cost and capital investment of soft or hard metal tooling, which obviously comes at a sort of a high initial cost. And also there are long lead times typically associated with those, because even before you started to cut tool or cut metal, there is generally or typically a sort of a collaborative design for manufacture number of cycles between the design house and the tool maker to just make sure that their process is suited and tailored to your geometry. But the great thing about this is that it's very, very quick. As James said, it's the kind of thing that can be turned around in a couple of days, and it's very low cost. In terms of actual time and investment, we'd be looking at the design time, so we'd be sort of talking a number of days to design the geometry and the tool. And then the materials and expenses of actually the 3D printing of the tool itself, plus some technical workshop support to get the calibration of the 3D print just right, and also with the setup of the injection molding tool. But the really, really great thing about this is that it really is tailored well to rapid iterative design cycles of geometry, allowing you to learn a huge amount very, very quickly through a quick evolution of different designs and geometry. So that's where this is very, very, very valuable indeed.
I think one of the real bonuses I've seen of projects using this technique is not only the sort of the supplier's lead time, the 3 to 6 weeks for a soft tool, but it's the to and fro between that supplier, where we go down to the workshop, talk to the guys on the floor, send them the CAD designs. I find that side of it is just so much quicker, and saves an awful lot of work.
Absolutely, and the other thing is it allows you to be, because there isn't that concern with expenditure for costs, capital costs and lead times, you can be more brazen with your design approaches.
Yeah.
And you in the initial sense, and so you can explore much more challenging geometries before you narrow it down to what really works and the sort of bare minimum and sort of essential elements that you need to get your design to work, which is very valuable, kind of from a designer's perspective as well. You're not too sort of constrained, if you like, in your approach.
And I think, just building on that, Tom, the other side of that is that when you do eventually go commit to metal tools, you're really confident that you've got something that you can mold, that is going to function, because you've been able to do that testing and that you've gone through all that learning already. So you don't have this sort of uncertainty that you normally have with the design, because you've already actually injection molded it, and that you can do correctly. You can go through that process, and it's created parts that you've been able to test and you've got confidence in. So I think that's a big step.
Absolutely, yeah. I mean, it's quite a privileged position to be in, having had molded parts in your hand and tested molded parts in the lab or with the rest of the assembly before you've even cut metal for production tooling. So that's a really big kind of value point of this process.
And Tom, can you share how many parts you can get off this process? And what depends? What dictates the tool life in this case?
Sure. Well, I mean, in terms of what dictates tool life, it's much the same sort of variables or features as you would find with conventional tooling. So we'd be sort of looking at the material types, the heat requirements of the tool, and those sorts of elements. And one of the considerations, I suppose, with this process is that per tool, you'd only be looking to get sort of 10 to 20 parts off, which isn't really a limitation, because again, one of the main benefits of this process is this rapid iteration. And so you really, for initial testing, only need a volume of that of 10 to 20. But additionally, if you do require more parts, as James mentioned earlier, you could just put another print on overnight and just have another tool the next morning, sort of thing. So
yeah, just building on that, Tom, I think often just a handful of parts is really, really valuable. That's enough to get most of the learnings that you would get. You don't need 50 or 100 parts typically to understand, does the design work?
Perfect. Josh, you showed us video of the actual sort of tool and that compressed from all sides taper tool. Can you use a normal tool approach with this technique, or and what about cooling circuits or things like that?
Not. I mean, it wouldn't really give you any benefits. It's similar in as much as you've got a bolster type approach, and that you can find that widely in industry. But it's normally your complexity is in the tool. To even if you've got simple-ish parts, whereas in this setup we have a very simple aluminium tool stack, and the complexity is in your 3D printed geometry, and the way that comes together and dismantles and assembles, and by putting it all you do away with that sort of the traditional complexity, as it were, and it allows us to move quite quickly and quite flexibly. So even from a design level, we don't necessarily have to go too far on the sort of DFM for injection molding, because you can just break the tool into another section, you split it again to relieve undercuts or to pull out sort of captive sections, and because at the time where we're using this, it's where we're trying to understand whether the principle of a mechanism might work, or that sort of more basic thinking. So it's not really in competition with that the sort of traditional tooling. It's sort of something slightly different.
What about cooling circuits? Have you ever incorporated that, or?
Not a traditional cooling circuit, but we do manage the sort of thermal properties of the tool. So resin itself is quite good at insulating the parts, so it stays hot for a long time. So the cooling cycle will be much longer on this. And on some materials that like to stay hot or hotter than others, that can be an issue. So what we do, we shell those 3D blocks. So we shell them out so they're hollow, and we use a low melt alloy inside, which is easy to handle in the workshop. They melt at sort of 100 degrees, and we backfill it with a low melt alloy to act like a heat sink, really. So the heat has because there's less resin, it has to pass through a smaller distance, and it's just soaked into the low melt alloy. And that really made a difference when we're developing the process. That allowed us or unlocked more materials for us. So that's how we manage heat.
And Tom, over to you. Have you done undercut features and inserts, other sort of more complex injection molding techniques?
Absolutely, yeah. I mean, the nice thing about the sort of fundamentals of this process and the architecture of the tool is that, as Josh mentioned, it's a 3D jigsaw. So you can simulate side actions or undercuts, which would be very costly in a conventional tooling method. And as you know, we sort of touched on a bit earlier, in your early design stages, the flexibility of this approach allows you to even create geometry which would be almost impossible to create using conventional tooling. So if anything, there's more flexibility using this approach. Obviously, any time we're designing something which will ultimately be designed through injection molding at a production level, that is always a consideration that's in mind. So we don't want to design ourselves into a corner. But if we are wanting to just test designs very, very quickly, what we can do with the 3D jigsaw is we can have a single component or elements within the 3D jigsaw which effectively acts a bit like a keystone. And as Josh said, when it's a manual process when you're removing the tool from the injection molding machine. And so what you can do is just remove this keystone component, and the rest of the parts will come away and fall apart. And so that's one approach that we can adopt. But it's the other thing that you can do, because you've got this sort of modularized tool, is you can also have you can simulate a twin shot process by removing and replacing elements of the tool. So if you've got a solid material substrate material that you want to overmold a elastomeric material on top of, a TPE, for example, you could potentially do that without removing all of the tool and just just shifting and replacing certain elements of it. So it's extremely flexible.
Perfect. Josh, back to you. We've heard a lot about the sort of features and the benefits. How would you describe the trade-offs here, and when you might choose different processes? Yeah,
sure. So I think time is a trade-off because this is a more labour-intensive process. The cycle times, if you were in mass production, would be very long. They'd be classed as really long, too long, really. So, but for us, we're really interested in making a handful of good components for testing. So the time sort of goes away, that time issue, but that is a big difference. And the accuracy of the resultant part is always going to be as good as the quality of the 3D print. So, I mean, these days, the SLAs that we typically use, they're very accurate and very good. But sometimes we do enhance the surfaces, but generally they're pretty good off the machines now. So yeah, your accuracy will always be underpinned by the technology that's been used to create the 3D printed part.
And are you doing any post-processing on, well, I guess the 3D printed mold itself, and or the part itself when it comes off? Do they need much fettling or finishing?
So sometimes we do some cleanup on the parts. The molds before we will always generally inspect them. Sometimes we'll 3D scan them. If it's like super critical, we'll do a bit of metrology on it before we've even molded to make sure that we've got a good print. And likewise afterwards we'll check the parts. But sometimes there'll be a small witness mark that needs cleaning up. It depends, because we're using this quite fast approach. It's quite geometry specific. but typically there's some cleanup involved, but nothing unusual.
Perfect. And James, maybe as a sort of to help bring some of this to life, maybe you've got an example of a project where you've used this technique and the benefit that it's brought there.
Yeah, so I think the one that springs to mind is a project we did recently where it was quite a challenging project in so much as it was looking at needle piercing, and it was needle piercing and design of a septum material. And that septum was in contact with a particular drug that had a particular requirement for the material that it was contacting. So there was a sort of drug stability risk there. And what we were able to do with this process, we were able to actually we came up with an overmolded prototypes. So we had a sort of a rigid housing in the right material, and then we were able to shoot the right TPE elastomer, which we were using as a septum.
Can you give any idea of scale, sizes, wall thicknesses of that?
Yeah, so it was. I think it was about sort of 25-30 mil long tube, which was the rigid housing material, and then we had a sort of I think it was a 6 mil septum. And there were two requirements really that we were interested in understanding as soon as possible. And the first one was, how does the septum behave with needle piercing? Does it tear? What force do you require for it to be pierced, and how much displacement is required to get a clean pierce? And then also, how does that material really behave with a drug? So we needed to do biocompatibility and in particular really drug stability testing. So in literally a week and a half, we had these parts in our hands, these overmolded septum material that we were then able to go into our lab and use our force stands and accurately measure the piercing behavior with a representative needle of these septums. So we could see how the septums deflected and how they were pierced by that needle and how much force was required. And then at the same time, in parallel, in our clean lab space, we could do some drug stability testing. And so we really quickly got an understanding of those two critical elements of the design, and were able to answer the project questions that were needed to be answered. Interestingly, what that meant was that actually it turned out that this concept actually did have some shortcomings, and there were some issues around the piercing aspect of that concept. So we decided to sort of stop that development path and then go down other avenues that we were also able to prototype with this technology. So I think what was really good is we got the learnings that we needed to really quickly. Within a couple of 2 or 3 weeks, we got answers to the key questions that then meant we were in a position to kill off that concept and switch our focus to something that was more more promising. So we could have done that had we got these parts made properly with metal tools. We would have also got the same answers, but we would have just got those answers maybe 3-4 weeks later. So I think for the whole development time and the risk, this process was really helpful in that project. And then the other aspect, or the other project that springs to mind is perhaps a project that, Josh, you can talk a bit more about, which was a really interesting project, which was a completely different application, but it was looking at emissions, radio or EMC emissions and antenna design. So, Josh, I don't know if you want to expand a bit.
Yeah, absolutely. So that was a home energy product, and we had two components to it. There was a sensor, there was some sensing, and that talked to a base unit that would record the sensor readings, and there was a radio signal between the two. And we were finding that during the development of the caseworks on sensor unit, we were finding that we were getting a loss in the signal, and we weren't really sure was it the geometry design, or actually was it the 3D printed caseworks? We were testing all our iterations in 3D printed material, and the 3D printed material we knew was hygroscopic. So we thought maybe if it's taken on some water, that's because it had to be that at that time that material had to be washed down once it would be as a post process. And we thought maybe that could be it, or maybe it's the geometry around the antenna area. So we use this digital tooling approach to just test it. So we were able to run the final material, which was a recycled ABS, in a digital tool and make our design in a final material and just go and test it. And we found out actually it was something to do with the geometry. We were a bit too close to the antenna, and it allowed us to redesign the area, try a couple of parallel concepts on the press, and remold it, and we de-risked that whole section. So we went into the end of that project was mass production. So we went into mass production with really good confidence that we knew exactly how that signal was going to perform, and it really de-risked the end of the process.
Yeah, excellent. I think that's the value of prototyping. You can simulate these things, but sometimes you really don't know exactly how it's going to behave until you've really got that physical validation. Okay, so those are the questions that we were going to run through. I've got a few questions in the chat, so if it's okay, we'll sort of run through these, and I'll see what we've answered already and how we can expand our answers for the others. So first question, I think we've covered this, but Tom, maybe one for you. How many injections or shots can you perform with such 3D inserts? Is it 10 or is it closer to 100? Maybe you could kind of give some of the limits that we've been through there, Tom.
Sure. So it would be closer to 10. I think again, depending on the material, if you're working with a particularly friendly material where you don't need high temperatures, you might get close to 100, but I think a safe margin would be sort of between 10 to 20, maybe 30. And that's sort of a typical throughput for each tool iteration. Sorry,
a follow on there. What do you think the biggest sort of factor is in that tool life?
I suppose it would be degradation of the tool and the alignment of the various different parts. So what happens is when it's compressed into the tapered pockets, you're sort of pushing all of the pieces of the tool together, such that they create a face seal between each element within that modular tool. So you're applying a decent amount of stress to each of those 3D printed parts, and you're also introducing heat. So there will naturally be some degradation to those parts, whether that be through creep or various, or alternatively, perhaps the alignment of each of those different elements doesn't quite match up as well as it did in the first initial batch that you did. So you might start to see some witness lines, and start to get a bit more flashing around those split lines on the tool itself. I don't know, Josh, if you want to sort of elaborate. You've probably also got a good gauge of what limits the.
I've tried to push them a few times. You're absolutely right. It's generally just stress. So when you're injecting, the cavity pressure is quite a lot sometimes for a 3D printed material to withstand, and we find that sometimes, especially near the where you're injecting, you get some crazing and some stress build up there, because that sees the highest amount of stress generally. But there's normally clues that it's starting to wear. You'll see slight, like a hairline fracture around that area, and as Tom says, that will slowly get worse.
Probably a good follow-on, actually. I'm just jumping around the order here, but what material is the 3D mold generally made from? And I think, Josh, you followed this one up earlier, but maybe you could talk about the 3D print plastic and then the insert, or the metallic core that we use.
Yeah. So we've tried all sorts of materials. We actually use a pretty bog standard resin from Formlabs. And it's quite nice because it's got a small degree of sort of ductility almost to it. So we found we tried some really hard materials, and they basically were good with temperature, but they fractured. So we use this one that's got a tiny bit of give, and we find that helps the parts bed in better together, and last a lot longer. And the geometry seems to be just as good, if not better, actually. And yeah, the sort of this hybrid approach of using a resin and a low melt alloy helped us to unlock a lot more materials.
Okay, a couple of questions here from here. It's what about the maybe Tom, over for you? Limitations such as wall thickness, cooling, or other things that are inherent in a non-metallic cavity. Yeah, what's how brave have you gone on wall thicknesses? And I note that Josh was quite keen on the iteration, which enabled us to push these factors sometimes.
Sure. Yeah. I mean, I'd say that's a fair question. I haven't pushed the limitations of the wall thickness myself using this process too far. But what sort of an example or a case study of a project that I worked on, if you like, was where we were looking to heat stake two films around a port, and that port had a sort of a tapered wing on it. The idea being that once those two films were sealed around the port, you effectively had a port and a bag. And so in an ideal world, what we would do is we would taper those wings down to almost nothing. So in one of our early designs, I think we limited it, or we had the thinnest part of the port at about 0.5 millimeter. And I'd say that was probably the extent of what we were comfortable filling. It was a very small part, it's fair to say. So it wasn't as though we were filling a thin wall section on a larger part. But we did get some good results filling, down to 0.5 mil in a small part.
Very good. And 2 questions here on post-processing we touched on earlier, but Josh, how easy is it to remove the parts from the housings? So that you talked about that manual ejection,
yeah.
And then maybe if you could cover the sort of post-processing typically that is needed.
Yeah, absolutely. So it comes out quite nicely. Because it's a tapered fit. It's tight until you only need a small amount of movement before it loosens off quite 100% sort of thing. It just comes away. So in the back of the pocket, there's some points where we can basically manually eject, just push a small rod through. That's enough just to break it out of the pocket. And then the molten plastic, or when it was molten, it's sort of filled the cavity, and that generally helps to hold it together a bit as well, just to assist us with manually releasing it. And we'll use mold release to help break it apart. So before we mold, we'll put mold release in, and then that helps us break it apart afterwards. Helps it lubricates the surfaces a little bit so they release. Yes, it's sometimes if the tool's wearing, you'll see some flash on on occasion on some of the witness marks where we've had shut-offs coming together. But it's generally, so when we design the tool, you do have half a mind about taking it apart again. So it's generally just a case of pulling parts in simple motion, and it frees the plastic.
Depends on a good design.
I think it's worth adding to that we don't have to go to the depth that you would have to think about the part design that you would with conventional injection molding, where you've got to think about, you've got to prevent undercuts and die locking, and you've got to allow the tool to open and the parts be ejected. So you don't have those at this point in the development cycle. That obviously that's quite a lot of thinking that has to be built into the design. But with this process, we don't really need to, because we're sort of taking it apart in blocks. We don't need to worry about that level of detail so much, and manually we're removing the part from the tool, so we don't have to concern ourselves too much with ejectors and a tool release and all this sort of thing. So I think it's a bit more forgiving in that regard compared to. I think
that's definitely part of the key to it, why it's useful, because it's such a simple approach and it can create quite complicated parts. So it really is very simple, by comparison. It's just blocks that are coming apart and put together there. There's no automation or complicated things that you'd normally think about in a traditional tool.
Okay, just keeping things, a couple of questions here. Do you ever find reasons for metal elements such as pins to form small holes? Tom, maybe one for you. I've seen some really successful inserts done with these components. I can remember for one project. Tom, maybe you could just give a quick answer for that.
Yeah, absolutely. I mean, I personally haven't worked on a project where we've used these, but I've seen examples sort of in the mix at CDP of projects where they've benefited from having a machined pin to get the sort of level of accuracy, or even just the geometry, just to be, if you've got a sort of a long span of a core pin, you'll get much more reliability in the geometry out of a machined component than you will out of a 3D printed component. But the other nice thing about integrating these sorts of components is that they're almost equally as rapid to manufacture. Just turning on a lathe, which we have that capability internally alongside and to complement our 3D printing. But additionally, if you have got a large cavity with a big span, they may actually benefit the assembly of the 3D printed tool itself. So they might act as a sort of a tie bar, if you like, so that when it's they're almost acting as sort of an alignment and a fit feature.
Good point. James, one for you here. I think you mentioned pierceable scepter. So someone asking here if we have any experience of moulding Topaz COC elastomer for pierceable scepter.
Well, bizarrely, yes, we do. That is a very specific material, but it does have some really great properties. And that's one of the grades that we have used in the past. So it's particularly resilient to certain drugs, and it is something that we've used or can use in our injection mold machine. So yeah, it's quite a new material, the Topaz COC elastomer, but it's got some great properties. So if it wasn't for that material, you might end up with a thermoset elastomer to get the particular properties that you're after. But with the COCs, that they're really great glass substitute materials, and they've got that very, very low permeability rates and very low or great material compatibility properties in terms of liquids that's contacting them. So they're really quite advanced in that regard. And yeah, that is something, a particular material that we've got experience of.
That's quite a nice example, actually, because when we were working with that material, because it's quite new, we didn't know, and there wasn't any information or any evidence from the material suppliers of Topaz's compatibility with other materials for overmolding. And so that was something that we could rapidly test, even just from a fundamental feasibility study, to say, well, this would really help us from a design and open up a whole load of design opportunities if we could overmold this material. Because of its infancy in the market, no one's got any evidence of its compatibility with other materials. So let's have a go. And that's what we were able to do, and very quickly answer that question and say, oh, actually, yes, it is compatible with other materials which perhaps have good stability properties. And then it opened up a whole realm of design opportunities, which was great.
And just picking up on that, I think, and you can imagine answering those type of questions would be really difficult if you're going to use simulation tools and analysis tools. I think you'd be struggling to answer those type of questions. But with this process, or using this approach, you can answer them quite easily, because you can just go and do it and see how it behaves. So I think, yeah, that was a
next question coming in. Just maybe you're not quite sure who's right for this one, but which will these parts be close enough to final parts from production tool to use them for design verification testing?
Interesting question. Possibly. It depends, because often we're doing it quite early on. You never know quite what the design's going to do, but so long as you've done some metrology, you've scanned and inspected everything, and you're using as close a representation of the final production, then it could be possible. The accuracy, if you're in the range of this process, the accuracy should be the same, and largely speaking, it should be similar. But it's probably a case by case kind of approach with that.
I think certainly you've got to be a bit mindful that if it's a medical application, typically you need to get to the point where the tools are inspected and validated. They need to be validated tools for sort of doing DVT testing. I don't think that's this process is suitable for that. So perhaps if it's a medical application, I don't think this is going to replace metal tooling. And I think this process doesn't really compete with metal tooling either. It's just trying to get you these early answers to questions early in the product development cycle.
That's a good sentiment. Last question, actually, I think, unless please keep typing away and we'll answer. Last question comes in about sort of what tolerance we can handle. It comes with a free offer of a CT scan. So maybe Josh, if you could mention the tolerances and how we handle that internally. But yeah, thank you for the offer, much appreciated.
The tolerance. So it's difficult to give you like a finite answer to that. So it'll be dependent on the geometry and the tool design slightly. Because we use this sort of multiple component approach, there'll be a tolerance stack up involved there. But typically, our approach to manage that is to 3D scan the parts the components before they've gone into the injection mold press, and we can do sort of we'll normally 3D scan them using like a GOM scanner, and then we'll do a comparison against the CAD to create a heat map and just check. What are we using? And that very much can depend on the results of that can depend on the geometry, the way the printer was set up. So it's a hard one to answer with a specific figure, I'm afraid.
I think there's two elements to it as well. I think, as you say, Josh, you've got the accuracy of the mold and how it's been printed, but then you've also got the accuracy of the part coming off that tool, which is partly down to things like shrinkage, warp, twist. It's all those things that affect injection molded parts, and that's where we do have the ability to use mold flow, but that's where perhaps you use a tool. If you really want accuracy, you might look at another tool such as mold flow to sort of compensate for things like warp and twist and shrinkage and so on. Which are as much, those really affect the accuracy of the final part as much as the actual how accurately the tool was made. Perfect.
Well, I think that's no more questions coming in, so I'll just offer a final chance for any questions. But other than that, thank you guys. Thank you for a good debate this afternoon, and thank you anyone. To our attendees, and especially to people that have asked some questions, enabling us to explain a bit more. So I think I'd like to sum up and just say thank you for listening, and that's all from us today. Okay, see you next time, I expect. Okay, cheers.
All right.